Welcome back. In this episode, we will discuss about the implementation of logic gates using 2 to 1 MUX. So we already know that the 2 to 1 MUX having two inputs and one output. So one of the input is selected for 0 and another input is selected for 1. So selection of inputs will be based on the control line or a selection line S. Okay. Subsequently, you will get the output Y. So this is the basic logic diagram. What is the logic expression this 2 to 1 MUX? Let us consider this is I0, I am name it as I0 and it is I1. So here Y is equals to, if S is equals to 0, this will be routed to the output. So here I0 into S is equals to 0 means that in SOP form, if S is equals to 0, you have to write S bar. S is equals to 1, you have to write S. Okay. Whatever it is the variable, for 0, you have to put bar. And for 1, no bar. Okay. So here I0 into S bar plus, if S is equals to 1, then I1 will be selected and it is routed to the output. So I1 into S. So this is the basic logic expression for a 2 to 1 MUX, right? Now we will design a NOT gate with the 2 to 1 MUX. So here I am trying to write a 2 to 1 MUX. This is the standard logic symbol. For 0 it will be selected, 1 will be selected like this. Okay. So in NOT gate, the logic diagram will be like this. This is A and the output is A bar. The complemented output will come here. Okay. So if you given 0, it becomes 1. If you given 1, it becomes 0. So the truth table is A, Y is equal to A bar. For 0, it becomes 1. For 1, it becomes 0. Right. So selection line S is equal to A. So selection line S is equals to A. If you feel S is equals to A is equals to 0, then 1 will come here. So coming 1 here is depends on by giving the input. If you give the input here, it is a VDD or a logic 1, then 1 directly comes here. So if A is equals to 0 given here and 1 directly comes here. So this is the output. Similar fashion, if S is equals to A is equals to 1 given here, then output is 0. So if you put here it is a ground or 0 volts or 0 logic 0, then obviously this 0 will be routed to the output and Y is equals to 0, right? So like that the output will be coming subsequently for the selection of the inputs. So a simple NOT gate designed using the 2 to 1 MUX. In similar fashion, you can design the AND gate. Now we will discuss about the AND gate with the 2 to 1 MUX. So the AND gate symbol will be like this. A, B are the inputs and output Y is equals to A dot B. Okay, the truth table will be A dot B, Y is equals to A dot B. So if 0, 0 output inputs, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. So this is the truth table. Now with this help of truth table, you can implement the AND gate with the 2 to 1 MUX. If you select the S is equals to 0, this will be selected. If S is equals to 1, this will be selected. Now what is the Y? Let us consider here S is equals to A is equals to 0. Irrespective of the B input, the output is 0. So the same 0 comes here. So directly you can write here, it is ground. So or logic 0. Logic 0, okay, or 0 volts. So directly this will be routed to the output. So Y is equals to 0. This is one case. Second case, so this will happen where S is equals to A is equals to 0, Y is equals to 0. Then S is equals to A is equals to 1. If S is equals to A is equals to 1, what will happen? This will be selected. Now here 0, B is 0, the output is 0. B is 1, output is 1. So you can write here B. B will be transferred to the output. So Y is equals to B. If you want to justify this truth table with the logic expression, you can easily taken care of. So here let us write this input is I0 and this is I1. So logic expression is S bar I0 plus S I1. This is the logic expression. Because for 0, this is S bar into I0 plus S into I1. Okay. For S is equals to 0, it becomes 0. So I0 is 0. So S bar into 0 is the input given plus S into I1 is B here. So instead of the S, what we have to do, what we have given A. S is equals to A is equals to 1. So it is A dot B. So AND gate truth table is the logic expression Y is equals to AB. So it will be satisfied. And another thing is also will be there. You can realize like this also. From this truth table, the min terms can be written here. This is M0, M1, M2, M3. Okay. So here what we have to do is, this is I0 and this is I1, and for 0, 1, 2, 3. Selection line we justify it is A bar and it is A. Okay. For a 0 term it is 0, and for one term it is also 0. So second term it is also there. Third term we have a 1. So just round it here. If inputs are not selected, it becomes 0. Here only at the 3 input only we have 1. So this I1 is actually B here. So here this I1 is nothing but B here. So it will be selected here I1 selected. So what happened is this A into B is AB. So like that also you can easily design the AND gate. So instead of the I1 you can put B here. Okay, so the term is B here. So A into B. Okay, A into 0, 0, 0 plus A into B. In similar way you can find the OR gate. OR gate with the 2 to 1 MUX. The symbol of the OR gate is like this. The inputs are A, B. The output Y is equals to A plus B. So logic expression is Y is equals to A plus B. And for the inputs of A, B, the output Y is equals to 0, 0, 0, 1, 1, 0, 1, 1. For these combinations, the output is 0, 1, 1, 1. Any one of the input is 1, Y is equals to 1, else 0. Okay. So if A is equals to 0 here, this 0 will be transferred. 2 to 1 MUX can be written here. So it is 0, 1, and the Y is equals to here selection line. If S is equals to A is equals to 0, then the B transferred here. So it is B. In case if S is equals to A is equals to 1, then if A is equals to 1, 0 irrespective of the B output is equals to 1. So directly you can put the 1 here. Okay. So 1 directly comes here irrespective of the B. So it is Y. So logic expression you can implement as here. Generally the logic expression is S bar into I0 plus S into I1. So S bar into I0 I have given B plus S is A and I1 is nothing but 1 here. So instead of the S bar you can put A bar B plus A. Okay. So this expression can be written as A plus A bar B can be written as A plus A bar into A plus B. This way you can write here. So this is a formula. A plus A bar, X plus YZ if we have. So it can be written as X plus Y into X plus Z. Similar fashion A plus A bar into A plus B. So A plus A bar is equals to 1. So that it becomes A plus B. Okay. So that the logic expression also satisfied here. And coming to another way, this is I0 and it is I1. Here we assumed that S is equals to A. So this A bar and A. And truth table, the sum of terms or min terms can be written as here M0, M1, M2, M3. So M1 is 1, M2 is 1, M3 is 1. So 0, 1, 2, 3. So 1 we have a 1, 2 we have a 1, 3 we have a 1. So if any one of the input is there, so you can write here it is I0. Okay. And here both inputs are selected so that you can write as 1. So from this diagram you can implement this is I0. Here I0 is equals to B. Okay. So I0 is equals to B you can implement, you can get here. Because I have already used A bar, so another term is B. So you can write B bar. It is 1. So in this way also you can easily design the OR gate with the 2 to 1 MUX. As simple as that. So we have already completed the NOT gate, AND gate, OR gate. Okay, now we will see the NAND gate. The symbol of the NAND gate is like this. The inputs are A, B, the output is equals to Y. So the logic expression is Y is equals to AB bar, we know that. AB inputs are there and the output is equals to Y is equals to AB bar. So for 0, 0, 0, 1, 1, 0, 1, 1 combinations we have to write 0 into 0, 0, 0 bar 1, 1 into 0, 0, 0 bar 1, 1 into 0, 0, 0 bar 1, for 1 into 1, 1, 1 bar 0. So any one of the input is 0, if any one of the input is 0, output is equals to 1, else 0. So this is the basic property of the NAND gate. So from this truth table, you can easily implement the 2 to 1 MUX. This is 0 and 1, output is Y, selection line S is equals to A. So if S is equals to A is equals to 0, irrespective of the input, output is 1. So here if you put here 1, so then 1 directly routed to the output, right? If S is equals to A is equals to 0, this 1 will come here. In second case, if S is equals to A is equals to 1, if it is selected this one, 0 will be transferred as 1, 1 will be transferred as 0, so that you can write as B bar. So B bar will be routed to the output, Y is equals to B bar. So here it is Y is equals to 1, here Y is equals to B bar. Okay. So the same expression you can implement here. Actually the 2 to 1 multiplexer is, treat that is I0 and it is I1 for the sake of simplicity. S0 bar I0 plus S I1. Okay, if S bar is here, instead of the I0 I have put 1 here, plus instead of the I1 I put here B bar, right? S bar means A. So A bar plus A B bar. Okay, so A bar plus A B bar means A bar plus A bar A B bar means A bar plus A into A bar plus A into A plus A B bar, A bar plus B bar, A bar plus B bar. So A plus A bar is equals to 1. That means 1 into A bar plus B bar is nothing but A bar plus B bar. So we already know that A B bar can be written as A bar plus B bar in dot product rules. In De Morgan's laws also you can implement like this. So this is also satisfied. Now another way to satisfy this NAND gate is write this as I0 and I1, and the selection line we have taken here A, so it is A bar and A, and the min terms M0, M1, M2, M3. M0 is 0, 1, 2, 3. M0 is 1, M1 is 1, M2 is 1. Okay, so both are selected here, so you can put directly 1. So that is I0 is equals to 1, and here I1 only selected, so it is actually it is I1. So actually it is I1. So A already we have used, I0 is equals to 1 we have written, and I1 nothing but B bar. Another term is B bar. Okay, because we assume that I1 is equals to B bar here. And with this table also you justify the NAND gate. With this expression also we justified the NAND gate, and with this logic diagram, with this truth table also we justify the NAND gate. Okay. Now we will implement the exclusive OR gate. Exclusive OR gate symbol is like this. The inputs are A, B, the output is Y. So Y is equals to A bar B plus A B bar is the output. So the truth table for this exclusive OR gate is inputs A B 0 0 0 1 1 0 1 1. So here for 0 0 output is 0, for 0 1 output is 1, for 1 0 output is 1, for 1 1 output is 0. So even number of ones or even number of zeros if you get, you will get the 0, otherwise it will be the 1. Okay. So from this truth table you can easily implement the 2 to 1 MUX like this. So selection lines are S, selection line is S and inputs are 0 1. See, if A is equals to 0, this 0 will be selected and 0 will be routed here. So B will be transferred to the output. So you can directly write the B value. So if S is equals to A is equals to 0, output Y is equals to B, right? If S is equals to A is equals to 1, if S is equals to A is equals to 1, this 0 will be converted into 1 and 1 will be converted into 0. That means inverted. So you can write here B bar. So Y is equals to B bar. It will be routed to here and Y is equals to B bar. So just we observe the logic expression Y is equals to, and it becomes I0 and it becomes I1. So S bar I0 plus S I1. This is the basic logic expression we will see. Instead of the S bar we put here A bar. Instead of the I0 we put here B. Plus instead of the S we put A. And instead of the I1 we put B bar. So A bar B plus A B bar. As simple as that. And also you can implement this. You can justify this thing here as like this. Here it is I0 and it is I1. It is A bar A. So for 0, M0 is 0, M1, M2, M3, min terms. So m1 m2 are the only ones. So this is 0 1 2 3. So we get the m1 and m2 are the ones. So where we are getting this is a, we will get here. So I naught is equals to a, and here, so I naught we get here, and here I1 we get here. So here I naught, instead of the I naught what we have put a, what we have given b, instead of the I1 what we have put here b bar. So a bar into b, a into b, so a bar into b, so here it is a bar into b plus a into b bar. Okay, this also satisfied. In similar fashion you can observe the exclusive NOR gate also. So this is the symbol of the exclusive NOR gate, a b, and y is equals to a bar b bar plus a b is the expression. Truth table is the inputs a b and output is y. For 0 0 it will become 1, for 0 1 it will become 0, for 1 0 it will become 0, for 1 1 it becomes 1. Okay, it's quite opposite to the exclusive OR gate. So here m0, m1, m2, m3. Okay, now implement the 2 to 1 MUX here. Implement the exclusive OR gate with 2 to 1 MUX. As usual will be like this. If s is equals to a is equals to 0, then inverted as 1 and 1 will be inverted as 0. So you can put here b bar. B bar is y. Okay, so y is equals to b bar. Second case, if s is equals to a is equals to 1, if selected this one, this directly comes b, b follows the y. So y is equals to b. So it becomes y. Okay, so y is equals to b bar and y is equals to b. So I am erasing this one. Let them see here the logic expression. Y is equals to, it is I naught and it is I1 actually. I naught into s bar plus I1 into s. S is we have written a bar a, and I naught is b bar now. B bar a bar plus I1 is b. Okay, so from implement you can write this one as a bar b bar plus ab. It is nothing but the output expression for the exclusive NOR gate. Okay, in similar fashion you can observe this one with this truth table also. So this is I naught and it is I1, it is a bar, it is a 0 1 2 3. For 0 for 0 we get 1 here, so round it. M1 is M1 M2 is not there, M3 is 1. So okay, so this is I naught and it is I1. So instead of the I naught we put here b bar. I naught is equals to b bar. Instead of the I1 we put here b. So a bar b bar plus a b. That's it. Now we will see the NOR gate. So the NOR gate symbol is like this: a b inputs and the output is a plus b whole bar. Okay, that is y. So the truth table is for a b 0 0 0 1 1 0 1 1. For 0 0 0 plus 0 0 bar is 1. 0 plus 1 1 bar 0. 1 plus 0 1 1 bar 0. 1 plus 1 1 bar 0. So in only this case only we get 1. Remaining cases it will become 0. So the diagram will be written here 0 1, the output is y. S is equals to a is equals to 0. So if s is equals to a is equals to 0, this becomes transferred as 0 to 1 and 1 to 0. So it becomes b bar. Okay, so y is equals to b bar. If s is equals to a is equals to 1, so it becomes whatever it is the b input, output is 0. So it becomes as 0 volts. So y is equals to 0 volts. So here logic expression and justification: y is equals to s bar into I naught plus s into I1. Instead of the s bar you can put a bar I naught plus a into I1. Instead of the I naught you put here a bar b bar plus a into I1 is 0. So this becomes a bar b bar. Okay, so a plus b whole bar can be written as a bar dot b bar in the De Morgan's laws. A bar dot b bar. In similar fashion you can justify this like this also. So it is a bar a and it is I naught and I1. So 0 1 2 3. Okay, this m1 m0 only selected, remaining all cases 0. So it becomes as I naught is equals to b bar and it is 0. So a bar dot b bar. a bar dot b bar plus a into 0. Okay, finally it is a bar b bar, which is nothing but a plus b whole bar. So like that you can implement any sort of the gate with the 2 to 1 mux.